Now, this tells us that it's very useful to count distance in standard deviations. And when you do that, you're counting in z-scores. You're converting the units into z-units. The z-score is normally distributed. It has a mean of 0 and a standard deviation of 1. Now, in practical terms, that means that when we're asked a question and we know that the mean is 0 and the standard deviation is 1, we can use z's instead of x's. Even if that is our random variable, we can think of it as z's. It is known as the standard normal curve. In other words, if z is allowed to range over its domain, it creates the standard normal curves for us. So before technology, when I was taking stats, we had these pull-out tables from the back of the book. We were allowed to bring them to exams, and our instructors looked at them to make sure that we hadn't written other stuff on them. But now we have technology, so we don't have to look up z-scores in a table. We look them up on our calculator. So here is geometrically what the standard normal curve looks like when we've got z-scores. I can use z if two things are true. If the mean is 0 and the standard deviation is 1. We're going to be using GeoGebra as our normal distribution calculator. It not only performs calculations, but also provides a graph that you can use to check that the area that you're finding or the probability you're looking for is correct. Let's start with an example by exploring the normal curve and finding the area under that curve. For example, a problem may ask you to find the probability that z is greater than 2. Now, a z value is from a standard normal distribution, not just normal but also standard. For a standard normal distribution, we know that the mean is 0, that means mu equals 0, and the standard deviation is 1, sigma is 1. Now notice that if we do not know the population standard deviation sigma and instead know the sample standard deviation S sub x, we'll use the Gossett student t distribution calculator instead. Thus, the probability that z is greater than 2 asks us how likely it is that a randomly chosen value in a normal distribution will be more than 2 standard deviations above the mean. To find the probability that z is greater than 2, we're asked to calculate a probability and enter 0 for mu and 1 for sigma. So let's pull that up and take a look. So here's our student t calculator, and this looks like, this is our normal distribution calculator. So because this is standard, the mean is 0 and the standard deviation is 1. We're asked to find a probability, so we select the Find Probability box. So we're finding a probability. We're also asked to a value of z greater than 2, so we select the right tail, and the lower bound is 2. And when we click away, it tells us the probability that we're more than 2 standard deviations above the mean. In other words, about 2.2750%. And in your workbook, I show you exactly how this looks inside of our GeoGebra application. Taking a look at the next page, we can see that if we're finding the probability that z is less than a boundary, we calculate the area to the left of that boundary by selecting left tail. Similarly, like in the previous example, if z is greater than the boundary, we calculate the area to the right by selecting right tail. If you have two boundaries, you're either interested in the inside area between the boundaries by selecting inside, or the area outside by selecting outside. Let's look at an example involving the heights of men. In this example, we'll explore real-world numbers. For example, college males have heights that are normally distributed with a mean of about 70 inches and a standard deviation of 2.8 inches. what is the probability that a randomly chosen blind date is over 6 feet tall? Well, let's get over the fact that you can actually have a randomly chosen blind date, and let's notice that there's two different units running around here. The question talks about feet, but the information was given to us in inches. So just to avoid too many decimals, let's keep everything in inches. So let's make 6 feet into inches. So to do that, let's pull up a calculator, and we say 6 times 12, so that's 72 inches. Now let's go into our normal distribution calculator. We're interested in a probability. Let's remind ourselves of the mean, 70 inches, standard deviation 2.8. So the mean, 70 inches, standard deviation 2.8 inches, and we're interested in looking for the probability that the blind date is over, that is greater than 6 feet, that is 72 inches. So we're interested in a right tail, but above 72. And the graph shows us exactly what is going on. Here's the mean at 70 inches. Notice that it's measuring the scale in standard deviations. So 2.8 inches more gives us our first standard deviation to the right. Another 2.8 inches takes us to the next standard deviation, and so on. So this table is already showing us that we're not all the way to the first standard deviation above the mean, and we're outside of that, that is further than that away from the mean. So our probability is 23.7525%. So we know that the distribution is normal and that the population standard deviation, so we can compute the probability using the normal distribution calculator. We handled the units, converting everything into inches. We then asked our question, what is the probability that x, that is the random variable, is greater than 72 inches, that is 6 feet, and we got our answer. Assuming that a blind date is, in fact, sufficiently random, the probability that a randomly selected male blind date would be over 72 inches is about a quarter. The normal distribution calculator not only allows us to find the probability that a randomly selected value from a normal distribution is in the specified region by selecting Find Probability, it also allows you to work backwards from an area or a probability to find the boundaries by selecting Inverse Normal. Sometimes we know an area or a probability and we want to know what x or z value traps that area to the left or to the right, and sometimes we even have an inside area centered around the mean and we want to know what values trap that area. These z values are referred to as z star, c sub 2, c, or z sub 2. They are critical values. So for example, let's confirm the empirical rule that 95% of the data is within 2 standard deviations. So let's pull up our normal distribution calculator. And since we're talking about standard deviations, let's do this in terms of z with a mean of 0 and a standard deviation of 1. We then want to capture inside a amount of area. So not a probability, we actually want to calculate that inside area. And we want that inside area to be 95%. So here is 95% of the area under the normal curve being captured with these boundaries. So this is no longer probabilities, these are actually locations on the z-axis. And notice they're very close to -2 and 2. And remember that because our standard deviation is 1 and our mean is 0, we're talking about z values, that means we're counting standard deviations. And we can see that we're almost to 2 standard deviations above the mean and 2 standard deviations below the mean. Recall that the empirical rule for 95% of the data is a simple way to recall that approximately 95% of the data in a normal distribution is within 2 standard deviations of the mean. We can use a standard normal distribution. Notice that we're simply counting standard deviation. So our mean is 0, our standard deviation is 1. We want to find the probability that a randomly selected value will be inside 2 standard deviations. That is, we want the probability of being more than -2 and less than 2. So let's go through and do it that way now. So let's find the probability that the lower boundary is -2 and the upper boundary is +2. And when we do that, we're finding 95.45% of the data, really close to 95% of the data in a normal distribution, is captured between -2 and +2. That is -2, that's 2 standard deviations below the mean. +2, that's 2 standard deviations above the mean. And of course we were still using inside, but now we were finding a probability. We see that the approximately 95% of the data in a normal distribution is within 2 standard deviations of the mean. In fact, we did that 2 different ways. Okay, let's look at another example where the data is generally normally distributed, and that is the length of human pregnancies. So we have a mean of 272 days and a standard deviation of 9 days. First, let's state the random variable. Of course, that'll be x, the number of days of a pregnancy. So this first question, we're going to refer back to our empirical rule. Find the probability of a pregnancy lasting more than 280 days. So let's just think about this for a second. 280 days is 8 days more than the mean of 272 days, and that's really close to the standard deviation of 9 days. So let's work through this that way. So we're talking about being 8 days above the mean or more. So that is slightly less than 1 standard deviation. Remember that 1 standard deviation from the mean in both directions contains 68% of the data. Let's go back there and look at the empirical rule. So the empirical rule says that 1 standard deviation to the left and the right contains 68% of the data. So we're talking about half of that. Half of that is 34%. We're basically now going to just talk about everything above the mean. So everything below is 50% and everything above is 50%. So we're talking about, if we think of the complement of what we're interested in, we've got 50% below and 34% above. So everything below 1 standard deviation is 84%, and I should say 1 standard deviation to the right is 84%. Now, that's what we're not interested in. That's why I said complement. So everything above 1 standard deviation to the right is 16%. And if you're saying there's got to be a way to calculate this, you're exactly right. Let's go into our standard normal distribution calculator and put in our information, 272 days and a standard deviation of 9 days. So the mean, 272, the standard deviation, 9. We're interested in finding a probability, and that probability is that a pregnancy lasts more than 280 days. So we want to be to the right of 280. So 18.7%, pretty close using the empirical rule. Remember, our empirical rule told us about 17%. We worked through this using the normal distribution calculator and found about 18%. Find the probability of a pregnancy lasting less than 250 days. Well, we've already got the mean and the standard deviation in. Now we're interested in a left tail because we're interested in it being less, and I've already forgotten 250, less than 250 days. So let's go in and enter that. And it looks like the probability of being less than 250% is less than 1%. So more than 99% of pregnancies are longer than 250 days, but to answer our question, What's the probability of a pregnancy lasting less than 250 days? And we'd have to say that that's 0.0073, less than 1%. Find the probability that a pregnancy lasts between 265 and 280 days. So we want an inside area. We want it to be 265 to 280. And the probability is about 60%, 59.4619% rounded. So we can write that as the probability that the random variable is between 265 and 280, and we can round that down to 59.46%. Now this next question is different. Find the length of pregnancy that 10% of all pregnancies last less than. We're not given a boundary, we're given a percentage, we're given a probability. So when we go into our normal distribution calculator, we're going to click on inverse normal because we want to work from a probability. This probability is 10%. We're going to enter that as a decimal, namely 0.1. And then we're going to ask the question, we're interested in 10% of all pregnancies last less than. That means that we're interested in talking about being less than that. So 10% of all pregnancies are less than 260.47 days. So let's say that in an interesting way. Notice that we don't have a known inside of our probability statement. The probability that x is less than that number of days d is, and there's our probability, 0.1. Well, that means that we're no longer talking about that probability being equal to something. We know exactly what that probability is equal to. It's 10%. But what we're interested in now is saying an equally valid implication. So if you haven't seen this symbol before, it's red implies, and it means that the next step is to determine what our unknown number of days d is. We just did that with the normal distribution calculator, and I think it's fair to round that to about 260 days. Let's take a look at it again. Remember, this is inverse normal. We had our mean and our standard deviation already. We were interested in being less than our boundary. That means we're to the left on the number line. We put in our probability and got our number of days. So now let's ask a question about whether it would be unusual for a pregnancy to last less than 250 days. Now, remember, we just computed what the probability of being less than 260 days is, and that was about 10%. So we're talking about a number less than 10%, but let's be thorough and let's calculate it. So let's go back in, and we're interested in finding the probability of being less than, was it 250? Yep. So let's put 250 in and see what that probability is. Now, oh, we did this one. This is the one that's less than 1%. And remember, the test for being unusual is 5%. And certainly less than 1% is less than 5%. So we can conclude that it would be unusual. Two more examples with the same mean and standard deviation. We're still talking about pregnancies. Find the length of pregnancy that the middle 40% of all pregnancies last within. So let's go back, check that our mean and standard deviation are still correct for the population pregnancies. And let's find inverse normal. We want to find those boundaries. We want 40% to be captured, and we want it to be captured in the middle. So that is around the mean. So let's look at being inside. So notice that the other option would be outside, but we're interested in inside. That is the middle portion. So it tells us that 40% of pregnancies are between 267 days and 276. Might want to round that up. So we can say that if we want to find those two boundaries that contain 40% of all pregnancies, again, we have already made our equation. It's equal to 40%. So we use the implies symbol to say that when we calculated this, that tells us that the lower boundary on the number of days, d sub 1, is 267 days. And the upper boundary, and it looks like rounding that up was a good idea, 277 days. So this next question asks us to find the length of pregnancy for the longest 15% of all pregnancies. Longest means that and greater. So we're talking about numbers to the right. So we're still interested in an inverse normal because we have a probability. The probability is 15%. So let's change our probability. And remember that we're interested in longest 15% of all pregnancies. So that's to the right on the number line, and you can see what it's shaded. That is, it's shaded 15% of the normal curve. That is to the right. And it looks like the boundary starts somewhere around 281 days. So again, we're looking for a boundary. So the probability that x is greater than, that is longer than, that boundary d for the number of days is 15%. That implies, when we use our calculator, d equals 281 days. Okay, let's look at a new example, and that is SAT scores. We're told that they're normally distributed with a mean of 514 and a standard deviation of 117. So let's put that in. We're using our normal distribution calculator. The mean was 514. The standard deviation was 117. And we're interested in, well, now let's start the questions. State the random variable. Well, that will be x, and it will be a randomly selected SAT score. Find the probability that a person has an SAT score over 700. Of course, over means to the right of, that is being greater than. So let's interested in finding a probability that we're right tail and that we're above 700. So it looks like about 5.6% of people who take SAT exams will earn a score over 700. So let's see how to write this. It's asking us what is the probability that that random variable for a randomly selected SAT score is greater than 700, and we rounded it to about 5.59%. The next question, find the probability that a person has an SAT score of less than 400. So less than, of course, is to the left. So we're interested in that upper boundary being 400. And it looks like about 16% of people who take the exam get a SAT score less than 400. So let's state that. The probability that x is less than 400 is approximately 16.49%. Find the probability that a person has an SAT score between 500 and 650. So we're going to go into our calculator. We're interested in the inside area. Between 500 and 650. So between 500 and 650. And it tells us that approximately 42.5% of people scores for people who take the SAT exam fall in that area. Find the SAT score that represents the top 1% of all scores. So first off, we're talking about the top, that is to the right, and we're talking about a probability, 1% of all scores. So we're going to change this to inverse normal. We're interested in finding that boundary that contains the top 1%. Was it 1%? The top 1%, yes, of all scores. And of course, top means that we're talking about a right tail. So out here you can see that little shaded region that contains 1% of our scores in this normal distribution, and that corresponds to a SAT score of 786 and change. So here we're trying to find that S for score. Previously we were using D for days, but now we're talking about SAT scores. So the probability that that score is less than X is, oh, that should be 1%. Okay, so we've changed that to the probability that S is less than X. That is, S is the lower boundary for those folks who are in the top 1%. It looks like it's about 786. Our next question, find the SAT scores that represent the middle 25% of all scores. So we are again looking at inverse normal, but now inside for the middle, and the middle 25% of all scores. So it looks like somewhere between 477 and 551. So we find those two boundaries for the scores, the lower end of folks in the middle 25%, 477, and then the upper boundary for those scores, 551. Find SAT scores that represent the bottom. So now we're talking about being less than and containing 30% of all the scores. So we're interested in being to the left of and containing 30%, 0.3, and it looks like that boundary score is 453 when you round. So let's state our answer. We're interested in the SAT score that is larger, that is the upper bound that contains a probability of 30%. It looks like that score is 453 when you round.